Alright, so now let's look at what happens if you have an object that is not infinitely far away but has a finite distance from the mirror. That means this S as an object distance, right, is not infinity, but some finite distance in front of the mirror. What we can do here is we can use ray diagrams to find the image position, and technically then what I have here is for this particular type of mirror, which is again concave mirror, right, you get then different different cases, different type of images. You can get, for example, in this particular let's say case that I have in front of us, I have an object at position P. That means you can see, right, object is further away from the mirror than this point C, which is the curvature of the mirror. That means I can say that S is greater than R. Okay, so S is greater than R. And in this particular case, if I then use ray diagrams, you can see, right, so I'm using two rays, 1 and 2. Look at the first one. First one goes and hits the mirror at the vertex, and then it reflects back. Second one goes from the object, like let's say this point Q, right? It goes through the center of the curvature. You can see, right, through this point C. And as it goes to the point C, it hits the mirror such that it's perpendicular to that and is then reflected back on itself. So then you can say that at this point, light is ray 1 is the, we're talking about this is a reflected, right? So 1 prime, which is the reflected light, and also 2 prime, which is that also reflected, right? And they both converge at that point Q prime. That means then what I can do here is I can take the, and use that to generate my image. And you can see, right, in this case, image is upside down, right? It's inverted. And it's smaller than, let's say, the object. And I can use that to find S prime, which is the image position. And then I can do some calculation to find, let's say, its magnifications and things like that. And one of the things I can directly even see without doing any calculations are two things. The image here is upside down, right? It's inverted. Image here is smaller than the object, and image here is in front of the mirror. That means I have a real image, I have smaller image, and I have inverted image. Okay? Because what I have here is all the real images are inverted. So inverted, right, is kind of like true or constant for all the real images. That means if your image has an opposite orientation compared to your object, that means that image is real. Okay? And all the real images for the mirrors generated in front of the mirror. Okay? Does it mean all the images generated by the concave mirror are real and small and in front of the mirror? No. So this is for this particular case. And we're going to see that especially for this type of mirror, right, concave mirror, you get different cases depending on the object position. And I have then this next example kind of demonstrating that. So think like this. So we have a concave mirror that has a radius of curvature equal to 24 centimeters. We're going to use ray diagrams to locate the image, if it exists, for an object near the axis at the distance of, then we're given four different distances for parts A, B, C, and D. One thing we have here is for sure that we know that there is a mirror there that has a radius of 24 centimeters. Remember, this is property of the mirror itself, regardless if there is an object there or not. Because it's a concave, the radius, point C here, is in front of that, right? And we can then take this point F to be half of that. That means focal length then is half of the radius, which is then 12 centimeters. Okay, so we can then also use that. Because one thing I can also do, which I forgot probably to modify that equation. Remember, the equation that we had for the mirror was 1 over S plus 1 over S prime was equal to 2 over R. But remember, focal length is then half of the R. That means I can rearrange this equation and rewrite where I have then 1 over s plus 1 over s prime equals then 1 over f. So that means this is then a modified equation for the, mirror equation. That means instead of the radius, you can use the focal length. Sometimes it's more useful to use this actually. Alright, so anyway, so we are given these quantities, and then we are told that there is a object, and what we have here is this object is basically has 4 different positions. And we're going to see, right, for each case, state whether the image is real or virtual, upright or inverted, and enlarged, reduced, or the same size as the object. So what we're going to do in this case, we're going to, for this problem, we're going to only use the ray diagrams to show that. And in the next problem, then we're going to do the calculation, numerical calculation for all of those values, let's say. Alright, so let's look at A. Okay, so for A, so this is the axis, this is the mirror. Remember then, let's say this is the focal point, this is the center of the curvature, and let's say this is where my object is. Okay, because for case, part A, right, what I have here is, you can see, right, the radius is 24 centimeters, which means focal length here is 12 centimeters, but my object P here is, object S is 55 centimeters, which means S is greater than the radius. Okay, that's basically my given values for this particular problem. Alright, so let's see what we have. So we're going to use 3 rays to define the image, and what I'm going to show you here is, let's say, how to find what type of rays to use to find the image. And there are generally, again, there are a number of rays you can use. So for example, let's say one that I always try to use is known as what I call them is P ray. P for parallel ray, because they move parallel to the axis, so they're parallel to the axis, and when they reflect, they go to the focal point. That means they always go to the focal point. Then I have what I call F ray. So again, so I call this P ray. So this P ray, all right. So the P ray is parallel then through the focal point. The next one is F ray, because it goes through the focal point and then parallel. Alright, and you can already see I have 2 rays converged at that point. So this point is where I have 2 rays already converging, but I can use another ray to verify that. Okay, and this third one can be either the one that goes through the center of the curvature, if it's possible, or the one that goes through the vertex. Either one is fine. So let's say let me show you that we can use the one that goes through the vertex. See, it goes like this through the vertex and reflects back like that. There you go. It also, intersects those at that point. Or the one that goes through the center of the curvature, which goes like this and reflects back on itself. You can see, right? All of them converge at that point. That means I can take that point, again, like let's say Q prime. Alright, so let me use this. Okay, so then this is where my image is. So for part A, it says, is it real or virtual? Well, what do you guys think? Remember, the real image is where the light rays move through that point. And I do have the light rays moving through that point, actual light rays. And it's in front of the mirror. So it is real. Upright or inverted? Well, obviously it is inverted. Then enlarged, reduced, or the same size? Well, here we can see that it is reduced. Okay, so that's basically part A. Okay, that means this is for this particular case. If the object is further from the mirror than the curvature, right? That means it has a S is greater than, let's say, the R, right? You have real, inverted, and reduced, let's say, image. Okay, so part B. Alright, so part B, it says the object is at 24 centimeters. Well, what else is 24 centimeters? Well, the radius is 24 centimeters. That means here we have object is at the curvature, right? At the center of the curvature. That means it's exactly same position as the center of the curvature. Alright, so what do we do here? Alright, so let's draw the mirror. And what I have here is focal point, C, and my object here is right there. This is my object. Alright, so let's do my ray diagram. Alright, so I can use the P ray parallel through the focal point. Then I can use the F ray through the focal point and parallel. What else I can do? Well, I can't use C because, you know, it is at C, right? But I can use a vertex. It goes like this and reflects back like that. That means more or less what I have here is all of those are converging somewhere over here. And what we can see here is then the object generates image that is right underneath the object. And is this real? Well, again, it's in the front of the mirror, so yes. Or you can say because actual light rays go to this point Q prime, so yes, that means it is real. While any real object is what? It's inverted. And in this case it is reduced, enlarged, or the same size. Well, in this case, same size. Okay, so for this particular case we get that. Alright, so let's look at then part C. It says object is placed at 12 centimeters in front of the mirror. Okay, so is that significant point? Yes, because that's also the focal length of the of this mirror. Here's what we get. So this is the mirror. Let's say here's point F, here's point C, and object is right here. Let's see what we get. Well, I can't use the F ray in this case, or technically I can, right? So, I mean, I can't use the F ray, but I can use P ray. Parallel, then through the focal point. And I can also use the V ray, right? The vertex goes and goes like this. And then I can use the C ray too, goes and goes like that. Now look at all those three rays that are reflecting. Do you see the pattern? Do you see how they're oriented? Well, they are parallel to one another. So they are parallel to one another, which means that they will never converge in front of the mirror. Well, if they're never converging in front of the mirror, that means there will be no image. That means if you stand in front of the mirror, curved mirror, concave mirror, at the same position as location as the focal length of that mirror, you will not see yourself in the mirror, because there will be no image. That's why that's a, you know, it's a case where the object is positioned at the focal length, and that's what you get. Right? So it's kind of amazing. Now let's look at the last one, which is at 8 centimeters. Here we have the image, object is at 8 centimeters. Focal length here is, remember, 12 centimeters. That means object has a less distance than focal length. Okay, let's see what happens here. Here's the axis, here's the mirror. Let's say, so this is focal point, this is curvature, and now my object here is, let's say, somewhere over there. Alright, let's see what we have. So what can we use? Well, I can use the P ray parallel, then through the focal point. I can use the V ray, hits the vertex, then reflects back. I can use the C ray, goes like this, then goes through the C like this. And what do we see? Is it same as, you know, the part C? Well, not quite, because here those rays, see part C, in front of the mirror they never, you know, intersect because they're parallel. If I trace them back behind the mirror, they're also parallel. For this one, if I trace them back behind the mirror, they actually intersect. That means if I trace them back behind the mirror, I kind of don't have enough room, but I can find the image right here in the back of the mirror, which means this image is virtual because it's in the back of the mirror. It's enlarged, right? It's enlarged. So basically it's virtual, enlarged, and upright. Okay, so virtual, enlarged, and upright. Why? Because object was placed much closer to the mirror than its focal point, and you generate basically an enlarged image. So you can see, right, this is 4 different cases for the concave mirror. Concave mirror gives you all of these different, combination. All right, so then let's go to the next example where, it asks you to calculate all of those values. So what is the magnification and image distance for all those 4 different cases? Well, here's then what I have. So this was the equation, 1 over s plus 1 over s prime equals 1 over f. Well, if you remember, right, this equation has very same format as the resistors in parallel or the capacitors in series. That means I can technically rearrange this where this can become like one of those shortcut equations. So this becomes, let's say, f is equals to then s times s prime over s plus s prime if I'm solving for the focal length. But if I'm solving for the, let's say, 1 over s, this becomes 1 over s is equals to 1 over f minus 1 over s prime. Oh, sorry, if I'm looking for the s prime, then I get that. And if I'm then solving the shortcut equation for s prime, this becomes object distance times focal length divided by object distance minus focal length. And this is generally my go-to guy for the image position for this type of mirrors and lenses. S prime equals s times f over s minus f. So I can always use this equation. That means, for example, for part A, remember the first case that we looked at, the focal length was 12 centimeters always, right? But s was 55 centimeters. So then if I'm using this equation, right, s prime is equals to then 55 times 12 over 55 minus 12, I'm going to get 15.4 centimeters, or roughly 15 centimeters for the image. And if you go back and look at the diagram that I had, the image was between the focal length and the radius of the curvature, which is, greater distance than 12 centimeters, so it matches. So the next one was for the position of the object to be 24 centimeters. That means it's now 24 times 12 over 24 minus 12, and we got then 24 centimeters. And this was the case where the object was positioned exactly where the center of the curvature here is, and then the image was right underneath, right, which is also the same distance as the object from the mirror. So that's why you get 24. You can see, right, s prime is positive, s prime for the first one positive and the second one positive, because both of those images were real in front of the mirror, and that means the image position is positive. So the next one was for the position of the object that was 12 centimeters. So 12 times 12 divided by 12 minus 12. And what we get here is 1 over 0, which is then undefined. That means there was no image. Remember, right? And then the last one was object was at 8 centimeters. So 8 times 12 over 8 minus 12. And what we get here is negative 24 centimeters. Alright, which means the image is in the back of the mirror. So that's why it's negative. Alright. So again, so let's say this is 1, 2, 3, 4, or like A, B, C, D. Excuse me. Then let's look at magnifications, which also should match what we had. So here, remember, there's magnification equation where you can do y prime over y. But there's also another magnification equation, which is negative s prime over s. That's using the geometry for those shapes. You can actually get this equation for the magnification. Negative image distance over object distance. So if I do it here, which is negative 15.4 over 55, I get magnification of negative 0.28. What does it mean? It means image is inverted, that's why there is negative. It means image is small, that's why m is less than 1. Let's look at second case. M is equals to negative, then I get 24 over 24, so magnification is negative 1. What it means is that magnification negative 1 means it's inverted, that's why it's negative. 1 means that 1 to 1. And again, you can go back and look at it, that matches. How about the third one? Well, m is equals to negative, well, it's negative infinity over 12. Well, that basically kind of, undefined, right? So you cannot, so undefined. Okay. So the last one, then magnification equals to negative, then negative 24 over 8. And what we get here, negative, negative cancels, 24 over 8 is 3. Which means image 3 times bigger than the object. Positive means it's upright. Alright, so that's kind of what we get for this. Alright. So, again, one last, thing we have here is the convex spherical mirrors. And remember, what we have for the convex is when the light, so this is the case where object here is infinitely far away. And in this case, what we get here is the light that is, incident to the surface reflects such that you can see, right? So 1, 2, 3, 4, 5. Look at those reflected rays. They all diverge away in front of the mirror. That means they will never intersect in front of the mirror. So where's the image then? Well, we have to, just like the plane mirror, trace them back in the back of the mirror, right? So let me use this color, right? So we have to trace them back, and when we trace them back, they intersect at that some point, and we can see that intersect at the focal point here. Well, that means image is exactly same as the focal point. But remember one thing. Focal length, right? So focal point, the way it's oriented here is in the back of the mirror. That means focal length is negative for the convex mirror. Radius is negative for the convex mirror. And we're saying s prime equals f. That means s prime is also negative for the convex mirror. Okay? So that's why the distance is negative. Okay? Distance is negative because focal length and radius for this convex mirror is negative. Okay. Alright, so how about if there is a finite distance for the object? Well, this diagram can help you with that. So what we have here is, here's the object, and this is the distance of the object relative to the mirror. And what we do, we use few rays. So let's say the V ray goes, hits the vertex, and reflects back. This is always the most useful one, I think. And then remember the one that has to go through the curvature C. But C is in the other side, so technically it goes and it appears to be going through that point, but then it reflects back on itself like that. So if you take this reflected and trace it back, and for the V ray, right, trace it back, you can see, right, you get then image generated over there. Image generated in the back of the mirror. So it is virtual. No actual rays going to the back of the mirror. That means, again, another way of identifying that it's a virtual. You can see, right, this is image position, image distance. And what we get here is, in this case, is in the back of the mirror. That means S prime here is negative. So what I can see here is also that image is smaller, and it's always going to be the case. That means spherical mirrors always gives you virtual smaller image, and that's it. There's no more other cases. Doesn't matter where the object is. It can be 10 centimeters, 100 centimeters, 500 centimeters from the mirror. You get exactly the same thing. Now then, what's going on here in terms of comparing the virtual image generated by the convex or concave? How do we know which one is what? Well, it's very simple. Convex always gives you virtual image, but whenever it gives you virtual image, it gives you a smaller virtual image. Concave can give you a virtual image in just one case, right? That last one that we looked at, where the object is placed closer than the focal length. And in that case, it gives you a virtual image, but it's always enlarged virtual image. That means you don't have, let's say, similarities in terms of the size. Yes, both of them are virtual. Yes, both of them in the back of the mirror. But convex mirror gives you smaller virtual image. Concave mirror gives you a larger virtual image. And that's how you can differentiate between them. All right. So again, kind of like, let's say, going back and reviewing, so you can say, right, you can use up to all of those 4 different rays. So the first one, again, I call this just a P ray. The second one is then it goes from the F, right? So I usually call this F ray. The third one, you can see, right, going to the C center, so I call this, I don't know, C ray. And then the fourth one goes to the vertex, so I call that V ray. So you have then 4 different rays that you can use, and usually you need no more than 3. 2 you can always use at least 2, right, to find the position where they let's say intersect, and the third one can verify that. Same thing with the let's say convex mirror. This is a little bit visually difficult because lights reflect, and even the light that has to go through the focal point or the curvature has to be kind of traced back. Because, see, the first one here is P ray. Because again, it's always parallel initially. But then it reflects like this. But remember, it has to go to the focal point. So then you assume that this reflected ray goes through the focal point like that. And then the V ray. So V ray is the easiest one, goes like this. And then we take this, and we can see, right, all of this 1, 2, 3, 4, none of those reflected rays will intersect anywhere in front. But if we trace them back, then you can see that they intersect. Generally what I use P ray and a V ray, so 1 and 4 to generate the image. And because, let's say, 2 and 3 is a little bit difficult, right? So the C here is, see, it hits the perpendicular, then it has to kind of, imagine that it goes to the C like that. It kind of bounces back like that. So again, you can trace it back. But, I think ray 2, right, which is the F ray, is a little more visually difficult to kind of draw. So that's why I usually don't recommend to using that. So use the V ray, the number 4, P ray, number 1, and then the C ray, which is number 3. Alright, so now let's solve some problems. Alright, so you have a dentist who wants a small mirror that will produce an upright image that has a magnification of 5.5 when the mirror is located 2.1 centimeter from a tooth. Okay. Now, should the mirror be concave or convex? Well, that's the question, because now what I want here is it wants upright image. Which image has an upright orientation? Virtual image has upright orientation. Well, that means concave and convex gives us upright virtual image. But then it says magnification of 5.5, which means it's enlarged virtual image. Which one gives us enlarged virtual image? Well, only concave gives us enlarged virtual image, right? That means in this case, tooth is our object, which is located 2.1 centimeters from the mirror, and it has to be the mirror has to generate 5.5 times larger image, which is upright. That means we have to use a concave mirror, right, where we get magnification larger, right? So that means positive large magnification in order to do that. All right, so we know then it has to be concave mirror, again, because we want a virtual larger image. So let's write down the values that is given to us. Okay, so we're given that magnification is 5.5, positive 5.5, right? We're given the object is located 2.1 centimeters. Okay, and now we know it's a concave mirror, and it's important because if it's a concave, we know that the radius here is a positive, right? The radius here is positive. That means focal length here is positive for those. Okay, even if the image is virtual. So part B is asking what should the radius of curvature of the mirror be. Alright, that means I need to find the radius. So one thing I can do here is I can use the equation where maybe at the end I can say the radius. Remember, radius is 2 times the focal length distance, right? So maybe I can use the mirror equation to solve for focal length and then use that to find the the radius. Usually this is what I would do, because it's this equation, right? Let's say 1 over s plus 1 over s prime equals 1 over f, where f is equals to then s times s prime over s minus s prime, sorry, s plus s prime. This is a little bit easier to use this equation. Alright, so I do have s, which is the object distance, but we don't have s prime. But we are given magnification, and we know that magnification is negative s prime over s. That means I can use this equation to find then s prime, which is then negative s times magnification. So negative 2.1 centimeters times the magnification of 5.5. By the way, if you noticed, I almost always use the centimeters. I don't really convert to meters, and you don't have to. For the mirrors and lenses, right? I don't mind, if you keep things in centimeters. All right, solving for s prime, right? So it's going to be 2.1 times 5.5. So I should be able to find the position for the image, right? So let's see, so let's say 2.1 times 5.5, I get 11.55 centimeters, and it's negative. Alright, so why is it negative? Because it's a virtual image. It's going to be in the back of the mirror. Alright, now that I have that, I can come back and use this equation for the focal length. So 2.1 times negative 11.55, then 2.1 plus negative 11.55. So if I do this, I'm going to get value for the focal length, which is going to be then 2.55 centimeters negative, right? And this then going to give me radius, which is then 2 times negative 2.55 centimeters, so which will give me negative 5.1 centimeters. Oh, sorry guys, sorry. There is no negative, because the negative cancel out. At the top you have a negative, at the bottom you're also going to end up negative, and they're going to cancel out. And this is a concave, right? It's a concave, and I told you from the beginning those values are actually positive. So that means the radius is 5.1 centimeters. Alright, so here's one more example. And for this one, what we have here is, let's say you probably have seen, right, in convenience stores and things like that, right? They have a mirror, that kind of curved mirror, where they see pretty much entire, room, right? So they can, the cashiers and things like that have a mirror. They can look at it and see basically everywhere. And that's a convex mirrors generally, because convex mirrors, take everything and minimize it, right? So they have a smaller virtual image, so they can have a greater field of view. So again, convex mirror is used in many stores to provide a wide angle of surveillance for the reasonable mirror size. Your summer job is at the local convenience store that uses the mirror shown. This setup allows you or the clerk to survey the entire store when you are 5 meters from the mirror. The mirror has a radius of curvature equal to 1.2 meters. Assume all rays are paraxial, means they are parallel. If a customer is 10 meters from the mirror, or how far from the mirror is his image. Okay, that means you're given a customer as the object, 1.2 meters from the mirror, and the customer is 10 meters from the mirror. You want to find where will the image be generated, right, in this convex mirror, and is the image in front of or the behind the mirror, and if the customer is 2 meters tall, how tall is his image. Alright, so let's do these calculations. Alright, so again, what we do here is we can use the equation. So let's write down what we're given. So I am given that radius is 1.2 meters. And remember, but this is a convex, so technically it's negative. That means focal length is half of this, or basically 60 centimeters. Or let's say 0.6 meters, because here we were given most of the stuff in meters. Then I'm given the position of the object as 10 meters. So then I can use this to find the image. Image will be, again, using this S times F over S minus F equation. So where I get then 10 times 0.6 over 10 minus 0.6. Alright. So, but the only thing here is focal length is negative. So, like that. Alright, so let's not forget that. Alright, so if I do that, then I'm going to get a position for the image as negative 56.6 centimeters, right? So like let's say, or if I convert to centimeters, I will end up with that value, negative 56.6 centimeters. Alright, so image is negative, means that image is virtual. Virtual image means it's in the back, or right behind the mirror, or in the back of the mirror. Okay, and then what I have here is for part C, that if the customer is 2 meters tall, how tall is the image? That means we're given y as 2 meters, and I want to find what is then y prime. Remember, y prime over y is equals to the magnification, which also equals to negative s prime over s. That means I can rearrange this and use the magnification equation, right, kind of like the middle guy. So then y prime is equals to negative s prime over s times y. Then y prime here equals negative s prime was negative 56.6, s was, well, let's say if it's 10 meters, right, so it's going to be then 1,000 centimeters, if I keep it in terms of, let's say, centimeters, right, and then times 2 meters, because this is centimeter, the unit is going to cancel out, and y prime will be 0.11 meters, or y prime here is 11 centimeters. Right, so that's going to be then in terms of the image position behind the mirror. Alright, so one more example dealing with mirrors. So a mirror on a passenger side of your car is convex and has a radius of curvature with magnitude of 18 centimeters. Another car is seen in this mirror and is 13 meters behind the mirror. Well, this is kind of like, it's behind the mirror. It's sort of like, let's say when you look at the mirror, it's behind it, but it's sort of like what it means is that the car is the object and 13 meters from the mirror, sort of like, let's say, in front of the mirror. So, and if this car is 1.5 meters tall, let's say its actual size, what is the height of its image? All right. So let's look at that then. That means we're given the radius as 18, but it's a convex, so that means negative 18 centimeters. That means focal length here is negative 9 centimeters. We're given that object here is 13 meters in front of it, and height of the object is 1.5 meter. For part A, we want to find the height of its image. Okay, so what is the height of the image? Well, to find height of the image, so the height of the image is equals to, again, just previous example, right? Negative s prime over s times, object height. So what I do need to do here is, again, since I'm given focal length and the object distance, I need you to first find this, image distance. So s prime is equals to s times f over s minus f. So then 13 meters minus then negative 0.09 meters, then divided by 13 meters, sorry, this is times. So 13 meters minus negative 0.09 meters. Okay. So if I do this calculation, I'm going to get negative 8.94 centimeters. Let's say if we convert to centimeters. So we get that for s prime. Then I can come back here and use this y prime equals negative s prime over s times y. So this negative is part of the equation. So then I have negative 8.94 centimeters divided by the object. So then this will be 13,000, right? Or 1300. So 13 times 100, right? So 1300, all right, centimeters. So centimeters cancel out, and then 1.5 meters. All right. So if we calculate this, then for the y prime we're going to get 0.0103 meters, which means it's 1.03 centimeters. So a very tiny image formed of a 1.5 meter tall car. So that's why your image, your car, like let's say mirror, right? The passenger side always has a warning. Objects in the mirror are closer than they appear. So that's why it says the mirror has a warning attached to the object viewed that it is closer than appear. Why? Why is this so? Well, because the height of the image, right, is much less than the height of the car, and when you see something that is smaller, it kind of appears to be, right, further away than actually it is. So that's why that warning is there to let people know that the car appears to be closer than they actually are. All right.